Hi, everybody. Welcome to join us for today's VeloDB webinar. Once again, I'm Shirley. So today we have two amazing speakers, as you can tell from our topic. And for the first half, we will have Rainer to shed more light on the compute storage decoupled mode of Apache Doris. And sometimes we just call it the decoupled mode for simplicity. And it's actually one of the biggest advancements of Apache Doris in the past year. And with it, we can make Doris a better fit in many use cases, especially for users who are already using cloud services or those who are looking for elastic scaling and workload isolation capabilities. And the speaker, Rainer, I think many of you already know him well. He is the Apache Doris PMC Chair, and he is one of the founding engineers of the Doris project, and he is a true community champion for Apache Doris. And for the second part, we have also invited Brian from the VeloDB team to show a demo of VeloDB Cloud, which is a fully managed out-of-the-box solution based on Apache Doris. He will start with the basics of using VeloDB Cloud, and then he will showcase how to perform cluster scaling and workload isolation with VeloDB Cloud, so as to visualize these features more intuitively. And I think this will help your understanding of both VeloDB Cloud and Apache Doris decoupled mode. So right now, let's hand it over to Rainer.
Hi everyone, I'm Rainer Chen, PMC Chair of Apache Doris and Tech VP at VeloDB. I'm excited to be here and talk about the compute storage decoupled architecture of Apache Doris. As many of you might know, the compute storage decoupled mode was officially released in Doris 3.0 around September last year, but actually its development started much earlier. After a long refinement, VeloDB contributed this feature to the Apache Doris community. We worked hard to fine-tune the architecture to ensure it's powerful and efficient. I'll be covering two key topics today. Firstly, I will introduce the technical features of the compute storage decoupled mode. We will explore its core design, key mechanism, and why it's a game changer. Then I will introduce some real-world use cases of it. Since the release of Doris 3.0, many users have asked whether the compute storage decoupled mode fits their specific workloads. Some have already adopted it and seen huge performance and cost benefits. So I'll go over some typical scenarios where the decoupled mode of Doris really makes a difference. Let's start with the architecture. On the left, we've got the traditional coupled architecture, where compute and storage are tightly integrated. This is a straightforward and widely adopted approach. In this mode, the front-end nodes, or what we call FE, handle metadata management and serve as the query coordinator. The backend nodes, or BE, store data with multiple replicas, usually 3 for high availability, and execute query fragments. In the middle is the current compute storage decoupled architecture of Apache Doris. What's different about it? Firstly, data storage is moved to a scalable, mature system like object storage or HDFS, so BE nodes are no longer responsible for storing persistent data. Secondly, instead of traditional BE nodes, the decoupled mode has compute nodes. The compute nodes no longer store persistent data, but instead rely on local caching to speed up queries. Thirdly, we introduce the meta service. A common question we get from the users is, what does the meta service component do here? Well, as you can see in the right diagram, our long-term goal is to make FE completely stateless. Currently, we are working to streamline FE, making it lighter and eventually merging it with BE into a unified stateless compute node. But why does this matter? As Doris scales up and the number of tablets grows, FE starts to hit memory limits. On top of that, when handling high-throughput real-time ingestion, FE can easily become a bottleneck. And that's because in the traditional coupled setup, FE handles all write transactions using a two-phase commit process. and everything has to go through the FE master. When ingestion workloads ramp up, this single point of execution slows things down. That's where meta service comes in. By introducing it, we offload a big chunk of metadata management from FE, which helps reduce operational overhead and makes Doris way more scalable. In the compute storage decoupled mode, since BE is stateless, we unlock true physical resource isolation at the compute layer. This means we can create separate compute groups, like you see in the diagram with compute group A and compute group B. These groups allow different workloads to run in fully isolated environments and make sure that compute and I/O resources don't interfere with each other. Now, when users first start exploring the compute storage decoupled mode, the first question they usually ask is, how's the performance? And that's a great question because moving storage off local disks and onto remote object storage definitely changes how data is accessed. Before we talk about performance, I'd like to break down the multi-layer caching system of Apache Doris for you. Let's take a look at the diagram on the left. It shows the different cache layers. The first layer is the Doris page cache. It stores the decompressed data. For example, when Doris stores data, it compresses it using algorithm like ZSTD or LZ4 to save space. But when that data gets cached in memory, it's already decompressed. Why does this matter? Well, in high concurrency queries, Doris can skip the extra step of decompressing data on the fly, which means faster query responses and less CPU load. The second layer is the Linux page cache. It holds compressed data. Now, the third layer depends on the architecture. In the coupled mode, it's the local disk storage. In the decoupled mode, it's cached data on local disks, but still compressed. And then we have the fourth layer, which is unique to the decoupled mode. It is persistent storage, where data is stored long-term in object storage or HDFS. In the compute storage decoupled mode, query performance can vary depending on how much data is already cached. It typically falls into three scenarios. The first one is a no cache hit. This happens when a query runs, but none of the cache layers have the needed data. So it has to be pulled entirely from remote storage like object storage or HDFS. This is the slowest case. But in real-world workloads, queries don't always hit cold data. Some data might already be cached. Or as queries run, cold data gradually becomes hot by being loaded into the cache. Over time, this improves the performance, and this is what we call the partial cache hit. So the third scenario will be full cache hit. This is like, in some cases, we preload the cache so that when queries start running, all the required data is already available in a memory or local disk. To see how the decoupled mode of Doris plays out in practice, we ran benchmark tests. The rightmost group of results shows the worst case scenario, where we clear all caches before each query, forcing every query to fetch data from remote storage. We can see that the decoupled mode runs about 30% slower than the traditional coupled mode. The middle group represents a more typical scenario. Queries start cold, but as they run, caching kicks in and performance improves. Now we can see when some data is cached, the performance gap shrinks to under 10%. The leftmost group is the best case scenario where data is preloaded into the cache before queries run. This allows queries to execute entirely from cache data. In this case, there's no difference at all between the two modes. Another question we often get is, how does storing data in remote storage affect real-time workloads? To answer that, let's talk about data freshness in the compute storage decoupled mode. This also brings us to an important design decision. Why did we introduce the meta service module? When designing the decoupled architecture, we considered two approaches. One is to store all metadata directly in object storage without a dedicated meta service. The other is to introduce the meta service to manage metadata separately. To compare the two approaches, we ran a benchmark using a real-time Flink ingestion workload. It was the 32 concurrent writes with a checkpoint interval of 5 seconds. Now, on the left is the throughput comparison. The green line represents the meta-service approach, and it reaches about 200,000 TPS. The yellow line represents the approach of storing metadata in object storage, and it only reaches 20,000 TPS. This means the meta-service module boosts the throughput by 10 times. Now, on the right side, we measure data freshness, which is the latency between when data appears in Flink and when it becomes visible in Doris. With meta-service, the delay stays at around 5 seconds. This is in sync with Flink's checkpoint interval. Without meta-service, the delay jumps to 50 to 60 seconds, which is a huge drop in real-time performance. Another common concern is the number of small files, especially for HDFS users and those using cloud object storage. Why is this important? In cloud storage, costs aren't just about how much data you store. They also include fees for operations. For example, on AWS, the delete requests are 10 times more expensive than the GET requests. So, keeping the number of small files in check is key to controlling cost. That's why we also compare the two approaches in this dimension. As you can see from the results, with meta-service, the number of small files is cut in half, compared to writing metadata directly to object storage. The compute storage decoupled mode brings three big advantages: lower cost, elasticity, and workload isolation. First of all, since storage is offloaded to cost-effective object storage, and compute and storage can scale separately, you're not overpaying for resources you don't need. Secondly, elasticity. Think about e-commerce platforms. During big sales promotions, they might need 2 to 3 times more computing power than usual. With a decoupled setup, they can scale up when needed and scale down afterward, keeping things cost efficient. Thirdly, workload isolation. This is super important for large companies running multiple business lines, or for users who need stable query performance. By separating read and write operations, heavy data ingestion won't slow down queries. This can ensure a smoother experience. So why the compute storage decoupled mode is a cost-effective solution? In the decoupled mode, only one replica of the data is stored in object storage or HDFS, which already has built-in redundancy. In contrast, the coupled mode typically needs 3 replicas of the data for fault tolerance, tripling storage costs. The slides reference EBS, which is block storage. In a coupled setup, you're paying for 3 data replicas, but in a decoupled setup, you only pay for 1 data replica, plus some caching costs depending on how much data needs to stay hot. So the decoupled model drastically lowers storage expenses. What's more, 1 data replica means tasks like data compaction, sorting, and I/O operations happen just once instead of 3 times. So it reduces the overall resource consumption by 2/3. That's about 70%. In addition, in real-world use cases, not all data is used every day or even every month. Over time, some data cools down and is accessed much less frequently. In the coupled mode, cold data still takes up CPU and memory, so it is kind of a waste of resources. One option for users is to separate hot and cold data across different machine types, but that's too complicated. But if you use the decoupled mode, things become much easier. Hot data stays in cache for fast queries, and cold data sits in low-cost object storage. And since query performance on hot data stays the same, the slight slowdown on cold data isn't a big deal for most workloads. The second big advantage of the decoupled mode is its elasticity. This is made possible by the stateless BE nodes. Since data is stored in object storage or HDFS, compute and storage can scale independently. This means compute and storage resources can be pulled separately, so you will have much more efficient resource management. If you're using shared storage or cloud storage within your company, you will have much less maintenance burden with the decoupled mode because you will either have a dedicated in-house team to handle storage or have the cloud provider to take care of everything. Elasticity also means the resources can be scaled up or down on demand, which is especially useful for handling traffic surges during big sales promotions in e-commerce use cases, for example. The third big advantage is workload isolation by different compute groups, and it is a key reason why many users prefer the compute storage decoupled mode. But it's not perfect yet because, as I mentioned, although BE nodes are already independent, FE nodes are still shared. That means if the FE of one compute group runs into issues, it can impact others. Our long-term goal is to make FE nodes stateless, so compute groups can be fully isolated in terms of SQL parsing, query planning, and execution. That said, shared storage will always be a common factor. If shared storage and multi-tenancy are well optimized, isolation works great. But if shared storage is set up on the fly without much operational experience, it might introduce some challenges. Up to this point, I've walked through the compute storage decoupled architecture and addressed some of the most common user questions, things like real-time performance and small file count. Now, I will introduce some real-world use cases we've seen from the community. After releasing the compute storage decoupled mode, a common question we heard from user was, our workload is purely online queries. We don't have cold data and we need low, stable query latency. So for our case, is the decoupled mode still a good fit? The short answer is yes. The decoupled mode can also benefit online business requiring low query latency. Take the user on the slides, for example. We compared their setup in both the coupled and the decoupled modes. In the coupled mode, they needed 6 machines on AWS with an upfront pricing model. But after switching to the decoupled mode, they only needed 3 machines. That's because, as we mentioned earlier, data ingestion and compaction processes consume about 70% less compute resources because there's only one data replica. On the storage side, traditional coupled architectures require extra buffer space to keep things stable. That means users need extra storage resources to avoid their usage rate from hitting 90% or 100%. The user in this example had already taken steps to cut costs. They leveraged the tiered storage capabilities of Apache Doris and used a storage setup of SSD and HDD. But after switching to the decoupled mode, they can still see a big cutdown in their storage footprint. Even the local cache size dropped because there's no need for 3 replicas now. Using the decoupled mode, you can also reduce your cost on historical data storage. In the traditional coupled mode, for historical data, even though you rarely use it, it is still costing some pricey server resources. But in the decoupled mode, you just put that data in cheaper storage like S3. This is an example of 200 terabytes of historical data, and you can see how much money they have saved. The third use case is in logistics. During big sales promotions, e-commerce platforms have to scale their resources 2 to 3 times to handle a flood of real-time queries from shoppers, like tracking orders or checking stock, or help merchants run consumer segmentation as part of their efforts to boost sales, and also support real-time inventory checks. Now, the fourth use case, you've probably seen this before. Imagine a company using a coupled system. Suddenly, they realize a certain machine type is less suitable for a specific task. But in the coupled mode, they have to add new machines, migrate all the data, rebalance everything, and then finally shut down the old machine. This process is like renovating a house while still living in it. But with the decoupled mode, this whole process becomes much simpler. You just add new machines as a separate compute group, and then you pre-warm the new machines by replaying old query logs. Once they're warmed up, you can redirect all new queries to the fresh compute group, and then you can just shut down the old ones. Next, let's talk about workload isolation. This is a must-have for big organizations. Imagine a big company with many product lines. Some are high priority while others are less urgent. They need to keep these workloads completely separate to avoid chaos. In the traditional coupled mode, they try to isolate these workloads by tagging resources, putting each product line in its own resource group. But here's the catch: data replication goes wild. If you have 5 product lines, you end up writing 5 replicas of the data. So although query traffic stays separate, the write workload becomes a bottleneck. But in the decoupled mode, you can isolate both writes and reads. If the high priority product line requires more resources, you can give it more BE nodes and cache. The next one is about isolating online and offline workloads. For example, you have offline tasks like heavy data processing or batch jobs, and you have online workloads such as the high concurrency queries or real-time dashboards where every millisecond counts. Then you might want to isolate them. In some cases, a user needs to guarantee a low latency for certain queries, and that's when they need the read-write isolation. With the decoupled mode, they can assign write tasks to one compute group and the query tasks to another. To sum up, the compute storage decoupled mode of Apache Doris brings lower costs, provides a better elasticity and workload isolation capabilities. On top of this, Doris has other superpowers like blazing fast concurrent queries, log storage and analysis, and data lakehousing. So all this makes Apache Doris a powerhouse platform for modern data needs. It has helped many users simplify their data stack. Previously, some users were using ClickHouse for analytics, Elasticsearch for logs, and HBase for real-time needs. Now they can unify everything under Doris. Fewer systems, fewer headaches. All right, that wraps up my presentation today. I'd love to invite all of you to join the Apache Doris Slack community. Whether you're curious about today's topics, running into implementation challenges, or just want to exchange ideas, you'll find our core developers and active users there. We are all eager to help. Thank you.
And thanks, Rainer. And like he said, if you want to explore further on the compute storage decoupled mode of Apache Doris, you're welcome to join our community on Slack, and I'll put the link in the comments. And in this community, we'll have a dedicated channel for this topic, so you can directly talk to the developers of the decoupled mode. And now for the next part, we have Brian with us. Hi, Brian.
Hi, Shelley. Hi, everyone. This is Brian from VeloDB, and it's really a great pleasure to have this session today. I'm very excited to share with you some cool updates of Apache Doris and VeloDB. And I've been working in data warehousing and the big data area for nearly 20 years as different roles like product owner and architect. In recent years, I mainly focus on promoting open source data analysis technologies, and I'm really impressed by how easy and cost effective of building a data warehouse solution based on technologies like Apache Doris. Yeah.
Thanks. Thanks for telling us about you, and welcome to be here again. And just now, Rainer has shown us the capabilities and applicable scenarios of the Apache Doris decoupled mode, which is a open source solution. And now, as we know, VeloDB Cloud is a fully managed commercial version of Apache Doris. So would you tell us the difference between them? Because if we already have Apache Doris as a powerful open source solution, when should we consider VeloDB Cloud?
Yeah, yeah, of course. First of all, it's really a good question, often asked by many users who are interested in Apache Doris. Yeah, to be simple, VeloDB Cloud, as you mentioned, is a fully managed cloud solution for Apache Doris. They are fully compatible. While VeloDB Cloud has more features to ease or enhance every aspect as a production-ready, cloud-native enterprise data warehouse. For example, VeloDB Cloud offers a more stable software core, which has undergone more tests. Yeah. And a management console to ease the system deployment, elastic scaling, failover, as well as daily maintenance and operations. VeloDB also provides an easy-to-use web UI for data developers. For most of these features I just mentioned, I can show you directly in the demo coming afterwards. And last but not least, VeloDB is the company behind Apache Doris. We provide service and support to safeguard our customers' systems. So if you are going to build a modern data warehouse in the cloud, VeloDB Cloud is definitely a better solution and worth a try. Yeah.
Thanks. And that sounds awesome. So now we
Mhm.
can't wait to see the demo. So please take it over from here.
Yeah. Thanks. Thanks, Shirley.
Now, I will give you a demo of how to use VeloDB Cloud. First, log into VeloDB Cloud via our web URL and come to the Management Console. Of course, if you are a new user, please first register one trial account. When you successfully log into VeloDB Cloud console, our first step is to create a warehouse. VeloDB Cloud has two deployment options, SaaS and BIOC. For SaaS deployment, it provides fully managed service out of the box, which eliminates the need of maintaining underlying infrastructure and avoids excessive investment in tasks like resource management, security control, daily operation, etc. It is more suitable for customers who want to focus on developing data applications rather than operating and maintaining a data warehouse by themselves. For BIOC deployment, it allows you to directly deploy warehouses in your own VPC, while data is also stored in your own cloud storage like S3. This option is more suitable for customers with strict data security compliance. In the center of the screen, you can see two buttons for you to try these two options. 14 days free trial for SaaS mode and a 90 days free service fee for BIOC mode. Below these two buttons, the New Warehouse button is for directly create a paid warehouse. Now let's click New Warehouse to enter the warehouse creation page. Enter warehouse name. Here we use demo. Select deployment mode. Here we choose SaaS. Select the cloud platform, region, and availability zone where the warehouse is going to be deployed. Here we select the AWS US West region and availability zone AZ1. Keep the core version as default. You can also choose other release version from the list according to your requirement. For patch version, or in other words, minor version, we recommend to choose auto upgrade to keep the system up to date. Table names are case sensitive by default. You can also change it by choosing case insensitive. Finally, click Create and wait for the warehouse to be created. Usually it takes about 1 minute. After the warehouse is created, we continue to create the cluster. Enter the cluster name. Here we input cluster 1. Select how many vCPUs will be added in this cluster. Here we select 8 vCPUs for demo purpose. Set the cache size. Here we just keep it as default, 200 gigabytes. Click Create and wait for the cluster to be created. This will take about 3 minutes. Okay, the cluster is successfully created. Before we can connect to the warehouse using Web UI, we still have two settings to be done. First, click Connection on the left sidebar and go to Public Link tab. Click IP Whitelist Management button and add your IP into the whitelist here. Then go to Settings on the left sidebar. Change your warehouse initial password. Now we can connect to the warehouse via built-in Web UI. Click Web UI on the left sidebar. Input your username and password to log in. Password is the one we just changed. In VeloDB Cloud Web UI, it provides various functions like SQL editor, session management, query audit, and so on. In Data tab, you can view your databases and table definitions. In Privileges tab, you can manage users, roles, and their authorizations. Finally, you can manage your data integration in Integration tab. In VeloDB Cloud, we provide some sample data for your test purpose. Here you can select sample data like TPC-H. Enter the integration name. Select the cluster and select the sample data size. Click Create and Load and wait for the data to be imported. After sample data is imported into your warehouse, you can run SQL queries on these sample data. Also, you can refer to our documentation to import your own data. Now let's see how to run a SQL query. Click SQL Editor under Query on the left sidebar. Select the database and the cluster which will be executing the query. Enter your SQL statement and click Run to get the result. In addition to Web UI, you can also use MySQL Client or JDBC to connect to the data warehouse. For detailed connection information, please go to Connection, Public Link. You can see they are all listed there. If you need a more secure connection, please refer to the document in Private Link tab. So this is a simple demo of how to use VeloDB Cloud. As you can see, it's super easy. Next, I will introduce some extraordinary features of VeloDB Cloud based on its storage and computing separation architecture. The first and most important feature is elastic scaling. VeloDB Cloud provides two ways to scale in or to scale out a cluster. One is manual scaling. The cluster computing resource and cache space can be manually adjusted to a specified size at any time. For example, here I want to scale out my cluster from 8 vCPUs to 32 vCPUs. Now you can see it's in scaling process. Okay, it's done. The other is rule-based auto-scaling. Currently, it can be based on time. At least 2 rules with different vCPU settings are required to achieve time-based elastic scaling. For example, you can add 2 rules: scale out to 32 vCPU at 8 a.m. every day, and scale in to 16 vCPU at 8 p.m. every day. By enabling this rule, you can get an auto-scaling cluster to achieve more cost efficiency. The second fantastic feature of VeloDB Cloud is workload isolation through multiple clusters. For example, now we have cluster A. We can also create another cluster B. Now we have cluster B created, and it can be used in following scenarios. The first scenario is workload isolation between different business departments. For example, cluster A is used for sales, like sales analysis. Cluster B is used for human resource, like employee statistics analysis. So physical resource isolation can be achieved between multiple business departments without interfering with each other. The second scenario is read-write separation. You can create a dedicated cluster for read workload and write workloads separately. Cluster A specializes in processing data ingestion, like insert and update, while Cluster B specializes in processing query requests to ensure a stable query latency for users. The third scenario is real-time and offline workload isolation. For example, for large-scale batch processing tasks, they can be assigned to Cluster A, while Cluster B is for real-time online analytics. Under these different scenarios, you can set different size for each cluster according to your requirements, and also start or stop them independently. Also, you can specify which cluster to be used in MySQL client, JDBC, and data import method streamload. Here is the example of how to specify a cluster in MySQL client. This is the example in JDBC. And this is the example when you use streamload as the data import method. For more details, please refer to our product documentation. The third highlight feature of VeloDB Cloud is disaster recovery deployment across different availability zones. We have launched this feature in regions such as AWS Singapore, US East, and Hong Kong under SaaS mode. This feature supports deploying the core components, including warehouse, metadata, and object storage, across multiple availability zones. So even we encounter a cloud service failure at the availability zone level, our data warehouse service will still be online as normal. Here we take AWS US East region as an example. When creating a warehouse, we can select all 3 availability zones to deploy our warehouse simultaneously. So the warehouse, metadata, and object storage will be deployed into these multiple availability zones. After the warehouse is created, let's continue to create a cluster. When created a cluster, you can specify different availability zones where this cluster will be deployed. For example, here we deploy cluster A into AZ, US East 1A. Deploy cluster B into AZ, US East 1B. After these two clusters are successfully created, for example, we can take cluster A as the main cluster, while take cluster B as the failover cluster. So when cluster A fails, we can rename cluster A to cluster X and rename cluster B to cluster A to ensure a smooth failover process. For more details about failover deployment, please refer to our documentation. At last, let me show you some other popular features of VeloDB Cloud. For example, system metrics. You can check key metrics of a warehouse or a cluster, such as CPU usage, memory usage, network throughput, as well as QPS, 99 percentile query latency, cache hit rate, etc. Furthermore, you can set alertings based on these metrics in Alerts tab to proactively monitor your cluster and keep it in a good state. Another popular feature is the billing center on the bottom left. There, you can check your monthly bills, as well as drill down to hourly details. VeloDB Cloud supports both cash deposit and attaching to your AWS or GCP Cloud Market deduction channels. Okay, that's all I want to share with you today. Hope you enjoy it, and you are very welcome to register VeloDB Cloud and give it a try. See you there. Thank you.
Thank you so much, Brian. And to summarize today's topic, we just present to you two options for fast data analytics with a compute storage decoupled architecture. And to try out these solutions, you can download the latest version of Apache Doris from the Doris website and join the Doris community on Slack. And then for VeloDB Cloud, you can register for a free trial on the VeloDB website. And that's all for today, and we hope to see you next time.